All right, today we're going to review the idea of the average rate of change and also introduce a new concept, the relative rate of change. Now, we talked about the average rate of change back in chapter 1 when we talked about linear functions. And we defined the average rate of change just to be the change in the independent variable when we change the dependent variable, right? So it's delta y over delta x, or in this case, as I have it written here, where we have y equals f of t, the independent variable is t, so we have delta y over delta t, okay? But it's just the change in the dependent variable over the change in the independent variable, okay? And it's basically the slope of a line between 2 points on a curve. All right, so today we're going to talk specifically about average velocity, which is just a particular application of the rate of change, right? The average velocity is the average rate of change of distance over time, right? It's the average rate of change of distance. So if our function is for distance and our independent variable is time, then the average rate of change of that function is the average velocity. Now, there is a difference between velocity and speed. Velocity is considered to be a vector quantity, and it's called a vector quantity because it has direction associated with it. Now, when you're talking about linear motion, the direction is just indicated by positive or negative. So linear motion, you could think of it as moving along a number line, and you're either moving in the positive or negative direction. So the direction for velocity that we're going to, at least as far as we're going to, we're just going to consider it as the positive or negative sign. So if you're moving in the positive direction, that means you're moving toward the positive end of the number line. Whereas if you're moving in the negative direction, then you're moving toward the negative end of the number line. So average speed is a little different. Average speed is the magnitude of velocity. All right, so it's essentially the absolute value of velocity if we're talking about linear motion, right? So if we just take the absolute value of the velocity, what we have is the speed. So we've taken away the directional component of velocity, and what we have left is speed. All right, so let's take a look at this first example. And we have a watermelon that's dropped from the roof of a building that is 125 meters tall. And the height of the watermelon above the ground is given by this function y equals 125 minus 5t squared. We're told that y is in meters, and time is in seconds. All right, first thing we're asked to do is just to graph this function. So what we can do is just plug in some values, right? We could choose some t values and calculate what the y value has to be. So you can see when t is equal to 0, we just have 125. All right, so I'm going to say 125 is about here. So that's our first point. And I could create a little table. I could do it over here, actually. Let's just make a little table of t versus y. And so 0, 125, if I put in 1 into the function, then I get 125 minus 5, which is 120. Plug in 2, then I get 125 minus 5 times 4, which is just going to be 105, and so on. So I'm just going to write these down. You can do the calculations on your own, but I'll just write down what I got for the calculations. All right, so 4 and 5. When I put in 4, I get 45, and when I put in 5, I get 0. All right, so I'm just going to plot those points. So 1 and 120, that's right there. 2, we're at 105, so we're just above 100 right there. And 3, we're at 80. Okay, and then 4, we're at 45. All right, these are going by 20, so it's about there. And then 5, we're at 0. All right, now if we connect those dots, let's see how well I can connect it with this pen. I'm not very good at drawing straight lines here, so I'm going to draw them in segments here. I guess it wouldn't be a straight line. It'd be a curve, but it's not going to be a very smooth curve. So, all right, so there we've graphed the function. I'm going to fix this one and just, there we go. That's a little better. All right, what's the domain and the range of this function? Well, we can just look at the context of this problem. This function really only holds once we drop the watermelon, and then the watermelon is under the force of gravity. So, so the t has to be greater than 0. And also, once it reaches ground level, splat, right? We're done. Assuming it's not going to burrow into the ground and fall further than ground level. So I'm going to say that t is between 0 and 5. Okay, so that's my domain. I could write that. But I'm telling you that the t is the independent variable. So by definition, if I just write t is between 0 and 5, that's probably fine, right? Now the range, right? That's the set of all. What? Range. Okay, range. The range is the set of all possible y values, right? The set of all possible outputs of the function. All right, so it looks like, because the domain is constrained between 0 and 5, then it looks like our range is just from 0 to 125. Right? 125. Okay, because that's the maximum up here at 0. At t equals 0, we get the maximum. T equals 5, we get the minimum at 0. All right, so there's our domain and range. And the next question is asking us to find the average velocity between t equals 1 and t equals 3. And explain the sign of your answer. All right, so the average velocity, right, is the average rate of change of distance over time, right? So it's going to be delta y over delta t, right? That's going to be our average velocity. It's rate of change of distance over time. So at 3 seconds, I'm at 80, right? So I'm going to say 80 minus the distance at 1 second looks like it's at 120. All right, and then I'm going to take 3 minus 1. Okay. Now, you'll see when I take 80 and subtract 120, I get a minus 40. And that's over 2. And I can reduce that down to a negative 20. Actually, I'm going to write it down here. Equals negative 20. And I'm going to include the units, right? Now, I know the units of this because the distance was in meters and the time was in seconds. This is meters per second. All right. Now, explain the sign of this. The sign is negative, right? So what does that mean? That means the velocity is negative. That means that the distance is decreasing for an increase in time, right? And that makes sense because it's falling toward the ground. So initially it's 125 meters up, on the top of this building, and the distance from the ground is decreasing, right? So I can say that it's negative because the distance is decreasing. Okay, I had to abbreviate my statement a little bit there because I ran out of room, but it's negative because the distance from the ground is decreasing over time as time goes forward. All right. Next question asks us to show on the graph the average velocity as the slope of a line between 2 points. So I'm going to see if I can grab a line tool here and draw a line, with a line tool instead of trusting myself to draw a line with a pen. All right, so we want the slope between t equals 1 and t equals 3. All right, so we're going to put a line here between 1 and 3. Okay, so there's a line that there's a line between those 2 points, and the slope of that line is the average velocity over that interval between 1 and 3. All right, so the next question asks, which is larger, the average velocity between 1 and 3, which is what we just found, or the average velocity between 4 and 5. All right, and then what does it tell us about the concavity of the function? All right, so let's draw another line. We got the line between 1 and 3. Let's draw a line between 4 and 5. Okay, so I'll put another, oops, now let's see, put it down here. I'll draw another line down here going from 4 to 5. All right, so now that line is, the slope of that line is, oops, there we go, is the average velocity. And so now it's also negative, right? It's steeper, meaning that it's more negative, okay? So it's more negative, which means that it's less. And that's where it gets a little confusing, right? Because you can see it's steeper, right? It's steeper. But the average velocity between 4 and 5 is more negative, so it's less. So to answer the question, then I guess the average velocity between 1 and 3 is larger. Okay, it's less, right? It's less negative, so it's larger. So technically, it's larger. So because the average rate of change is decreasing as time goes forward, the graph is concave down. All right, so the graph is concave down, which is what you can see from the graph, right? You can see that it's curved in a downward direction. So, you know, it's like an upside down U. It's like the right half of an upside down U. So it's concave down. So you can see that from the graph, but you can also see it from the fact that the average rate of change is decreasing. So, but keep in mind, this is kind of why I put the idea of speed in here as well, is that it actually is getting faster as it falls toward the ground. The speed of the object, the watermelon, is getting faster, but it's becoming more negative. So the speed is greater, right, from 4 to 5 than it is from 1 to 3. But it's more negative, so it's technically less, and thus is concave. You know, the function is concave down. All right, got one more question, is interpret the concavity of this function in the context of this problem. All right, so we know that the concavity, you know, it's concave up. Concavity has to do with the curvature, right? And if the rate of change is increasing, it's concave up. If the average rate of change is decreasing, then it's concave down. Here we're talking, the average rate of change is average velocity, right? So when we talk about velocity increasing or decreasing, right? Increasing velocity is acceleration, right? Decreasing velocity would be deceleration. And so because the rate of change velocity is acceleration, then the concavity corresponds to the acceleration of the object. Now in this problem, the velocity is negative and it's becoming more negative. So it's effectively accelerating in the negative direction. In general, if velocity is increasing or speed is increasing, it's acceleration. But here we have acceleration in the negative direction. So even though the velocity is technically decreasing, the speed is increasing. And so it's accelerating in the negative direction. And so it is getting faster. It's going faster and faster as it's falling until it hits the ground. So, all right. So the main points here were applying rate of change, right, the average rate of change, to a function for the distance over time, right? And when you find the average rate of change of distance over time, that's velocity. All right. Positive, we have positive and negative indicating the direction of the velocity, and the absolute value of velocity, meaning we take away the direction component, we get speed. All right, I will meet you in the next video.